Now we're going to look at some useful notation in groups and mistakes to avoid. Suppose that A belongs to a group G with operation star, and let n and m be positive integers. Then the exponential notation you're used to really works with groups too. So for example, A raised to the n power, we write to mean n copies of A all being multiplied together using the operation of the group G. And multiplying, or writing a to the n times a to the n in our normal exponential notation really means a to the m times a to the n. And so what you have is m plus n copies of a in the group G. Furthermore, a to the n and then raised to the n power means the same thing as it did using exponents. So that's m times n copies of a, all being multiplied together using the operation of the group G. Now also, a to the minus n means n copies of a inverse multiplied together using the operation of G. And therefore, we write a to the 0 to mean the identity of the group G, call it little e. So in that manner, a to the n times a to the minus n really means the identity in the group G. So that's useful notation. Furthermore, in a group, inverses are unique. So to prove that, suppose that A is an element of G again, and let's let H be equal to A inverse. Then remember what that means is that H times A is A times H, which is the identity in the group G. To show that this is unique, suppose that K is also an inverse of A. So say K times A is A times K is also the identity of G. Then what we'll show is that K is the same as H. So this will mean then that A times H, which is the identity in G, is the same as K times E, or KAH, which is the same thing then as the identity in G, because that's what K times A is, which is H, and E times H is just H. And of course, this is just K. So in this situation, on left multiplying by K, we get H. Similarly, if we right multiplied by K in this equality, E is HA, then we'd write that's KAH is K, or in other words, this is K, and of course you know this is then combining A and K, this is E, so this is HE, which is H. So inverses in a group are unique. And finally, this is convenient notation. If you have a product of elements in a group, so say that now A and B are elements in the group G, and we are interested in finding out what is AB inverse. So what is the inverse to the product of A and B? Then it turns out that the inverse here is actually given by B inverse A inverse, not A inverse B inverse, unless the group happens to be abelian. For example, we can show this as, well, let's look at what A times B inverse A inverse is. These elements belong to G, so each one of their inverses are there. Well, this is the same then, since the operation is associative, as writing A, B inverse, and then A inverse, which is the same here as A. This is the identity of the group, and then A inverse. And of course, this times A is just A inverse, and so then we have E back. So on right multiplication by this element, B inverse A inverse, we get that times AB as the identity. Similarly, if you go the other way, which you need to in order to show that this element is a two-sided inverse, you'll find a similar situation. That done this one way, B inverse A inverse times AB, playing the same game, is B inverse A using associativity, which is B inverse EB, which, as you know then, this is the identity. So therefore, we can conclude that AB inverse is given by B inverse followed by A inverse.